Hello. Hello, Supriya. Hi. Am I audible?
Yes, hello.
Hello. Hi. Yeah. So I think
Yes, you are
we'll
audible.
join. So we'll wait for another 2, 3 minutes and then we'll start.
Yeah, okay.
Hello. Hi. Maybe the others are not going to join.
Hello.
Yeah. So I think we'll start off. Let others join later. So
Yeah.
good evening once again, Supriya, and welcome to today's tutorial session on urban utilities planning, water supply, sanitation, and drainage. So since you know how this goes, so without much introduction, I'm going directly. So this is today we will be discussing about week 10's certain questions and numericals. Two numericals we'll discuss, and then other some theory parts. So these will be mainly based on whatever we discussed in week 10, that is on sewer appurtenances, different appurtenances which are used, stormwater drains, how do we design them, and the sewer maintenance and cleaning, what are the factors that we need to consider, and laying of sewer. One sec. Yes. So, and laying of sewer and utility corridors. So let's get started. Uh, Yeah, so so this I'm skipping. So let's directly jump on to a numerical. Uh, so the question is, a triangular gutter of concrete has a longitudinal slope of 1% and cross-sectional slope of 2% and a curb depth of zero point 0.2 meters. The flow rate and flow depth, if the spread is limited to 2 meters, are respectively. So you've been asked to find the flow rate and flow depth. So why is it a triangular gutter? Again, the question starts with a triangular gutter. So why do we design triangular gutters? Any observations? Hello. Hello, Supriya. Am I audible?
Yes, yes, you are audible.
Yeah, so so why do we have triangular gutters? Is there any particular reason for that?
We get maximum vertical length.
Yeah. Okay. So basically, we want water to slope down and fall into the gutter, and through that, through the drain, we want water to come to the channel which is used to, or the stormwater drainage channel which we have designed. So mainly in roads or pavements, we would observe that we would have a curbstone, something like this, like if we have a curbstone, and then there'll be a gutter which is sloped, and sometimes there'll be an opening here so that water slopes down and falls. So sometimes there's an opening here and water falls down into the drain this way. So mainly we always talk about a triangular. Yeah. So mainly we always talk about a triangular gutter. So here the question is asking what should be the flow rate and flow depth. So flow depth means this distance, that is this one, or y, whatever we call it. If the spread is limited to, by spread, what we mean is the width, or this much, like what is the overall width of the gutter. So if that is limited to 2 meters, then what should be the flow rate and flow depth given, sorry, if the slope is already given, so this angle or the slope is already given, so two types of slopes are given. So we have been given a longitudinal slope and we have been given a cross-sectional slope. So what will this slope be if you're looking at a gutter, something like this along the road? Is this a longitudinal slope or is this the cross-sectional slope that we are talking about in this particular section? Anybody?
This is longitudinal slope.
This is a longitudinal slope is what you're saying.
Yeah.
Okay.
And what
Okay. And what will be the cross-sectional slope then?
cross sectional? 1 second. I'm getting confused.
Yeah. Okay. So this is actually the cross section because you're talking about so if you have a drain like this, that is the overall drain, and you have the gutters over here. So it's through these gutters that water is entering inside. So as I said, it can either be on the sides or it can even be the gratings can even be over here. So that we have discussed in our lectures. So let's imagine that this is the road, and from this road water is going into this side and the drain is located over here. So if that is the case, this the whole the whole length of it, if we cut something like this is the longitudinal section, A dash, that will be the longitudinal section. Whereas if
Yes.
we take a cross-sectional cut, B dash, that is a cross-sectional section. So here we are mainly
Yes.
talking about the road and the drain. So we are actually looking at B dash. So this section, what I've drawn over here is actually the cross-sectional section, not the longitudinal section. Okay, so we have a cross-sectional slope of 2 meters, which means this slope, that is Sx is equal to, not 2 meters, sorry, 2 percentage. That is the cross-sectional slope, which is 0.02 is the cross-sectional slope that we have. Now we have a longitudinal slope. So as discussed, that A dash, which is the along the overall length, whatever slope we are having, that is the longitudinal slope, which is given to be, that is L, we denote it by SL, which is equal to 0.01. So this is the information which is given. And yeah, and a curb depth of 2 meters. This information is also given. Maybe we don't need, so curb depth means this is the curb depth which is given, 0.2 meters. That is the, sorry, this one, the curb, the depth of the curb. So that is also given. So, but let's see what is the information that we need in order to calculate this. So, so we've been asked to find two things. First one is the flow rate, and second one is the flow depth. So flow rate, we have always discussed, like how do we calculate flow rate? Mainly we use the Manning's equation, usually in the previous ones, in order to find the rate or the quantity and velocity and all, we were using Manning's equation. So this is like a derived portion of Manning's equation, or a modified Manning's equation, which we have learned in our previous, in the lectures which we have learned. So we will use that equation. So that's a modified, so basically Q is what we need to find, flow rate. So to find, we will use a modified Manning's equation, like from that. And to find the flow depth, what do we do? So it's a cross section. So we know this slope, we know, that is x, yeah, Sx we know, y we are asked to find y. So we can just take the division, that is from the slope equation, like, sorry, yeah, from the slope. So slope, and with this width also we know, t, which is 2 meters we know. So we can find y is equal to t into sx. We can write that, right? Like from this angle, the normal. So that is how we will be finding the flow depth. So let's start by finding the flow rate. So the formula for that is this modified Manning's equation is given by Kc divided by n Sx the whole raised to, sorry, 5 by 3 into Sl the whole raised to 1 by 2 into T raised to 8 by 3. So this is the equation. It's We have learned this in our slides. So this is the equation that we will be using. So what is Kc over here? So Kc is nothing but it's just a constant. So it's called an empirical constant, empirical constant. And the value of that, which we will always be considering for this, is about 0.376. So this formula you might have to memorize for your exam point of view. So this is the empirical constant, and n is Manning's roughness coefficient. So Manning's coefficient, and Sx, Sl, and T we already know. So we can just plug in the equation and then get the value. So I'm just putting in 376 divided by n, which is yeah. So Manning's coefficient, we usually assume it to be about 0.012. So this also you might take a note, like for the in the assignment, this time's assignment also, you can assume this coefficient, that is 0.012. So 0.012 into Sx, which was 0.02 in raised to 5 by 3 into Sl, which is a longitudinal slope, zero point zero 0.01 raised to 1 by 2, and T, which is 2 raised to 8 by 3. So what does this work out to? I'm not checking the chat box. Is the answer in the chat box? Okay. Yeah, so what If you're getting the answer, you can put in the chat box, you can speak it out. Anybody answer? Okay, so you might check. So this works out to 0.0293 meter cube per second. So any difference in opinion, anybody?
You can move forward.
Okay. Did you attend yesterday's lecture, the live session?
No,
Okay, okay, fine.
but I have done the assignment.
Oh, you've completed the assignment, so okay. Yeah, but you can do the calculation simultaneously, so it'll be good. Like an interactive session would be much better
Yeah.
also, right? Yeah. So
Yes.
okay.
Yes.
So let's assume we got this value. The next part, which is to find the flow depth, which we can do it as y is equal to. So t is again 2. So this is very easy into 0.02, 0.04 meters. So this should be y. So this should be zero point zero 0.04 meters, and the overall the flow rate, the quantity of flow which can be there is 0.0293 meter cube per second. So that was, so this question is there in the, a similar question is there in this time's assignment also. So might make a note of this. Fine. So any doubts, anybody? I'll wait for like 30 seconds.
No doubt.
Okay, I'll proceed then. So this time's content is actually a bit easy. Like, so we'll go a bit slow also. Yeah. So second question is we have to match the following. So different. So questions have been asked about manholes, dry pit system, flap gates, and check dams. So what do these? What is the definition for these? Is what the question is asking. So Supriya, do you want to take this question up?
Yes.
Good.
P is 3.
PS3 manholes connects ground level to opening in sewer line for maintenance. Yes, correct.
Check dams will be second. Is second.
Okay, check dams is small temporary structures constructed before a swale across a drainage ditch to reduce runoff velocities. Yes, right.
And then dry pit is and flap gates. 1 second. Flap gates is R is 4. So Q is 1.
Okay. Okay. Flap gates is reduces inflow in coastal sediment sand tidal. Yeah. So flap gates is right. So basically, along the inflow which is happening, you put small gates like this so that rushing water, all the sediments get deposited there and only the water would come in. So those are flap gates. And Q, the dry pit system, is horizontal centrifugal pump is installed with a suction pipe connected to the sump and outlet at the desired outfall point. Yes, so that is a dry pit. So we have learned this, like what is wet pit and dry pit, two types of pump installation methods. So in wet pit, there is a chamber, there'll be a suction unit over here, water will be sucked, and the motor is placed in within this chamber itself. Like there's a segregation in the chamber and the motor is placed inside. But in a dry pit, there's a pump and there's a suction pipe which is happening, but the motor is placed outside. Like this will be where the motor or the pump is placed. Here it's placed inside. So that's the difference. So that's why it's said that the centrifugal pump is installed with suction pipe connected to the sump and outlet at the desired outfall point. Right. So yeah, so that is right. So this works out to which one? Option A, right? So option A is the answer for question 2. 3, 4. Yeah, correct. Very good, Supriya. Yeah. So let's proceed further. Question 3. Stormwater facilities has to be inspected regularly for scoring of beds and sites, full or partial blockage of the drain, and damage to drain structure. So, do we have to inspect it for scoring of beds and sites? Like, is it required?
Yeah, A is correct.
A is correct. Okay. Full or partial blockage, is that required?
Correct. A and B is correct. C, I think it's wrong.
You're saying C is wrong. Damage to the drain structure. So, okay. If so, how do you say? How
Can
do you propose that damage to the drain structure can be found out?
yeah, through inspection only, I guess, but I'm not
Yeah.
sure.
It is, it is. So basically, inspection, we have learned that two types of inspection are there. That is, it can be physical or the manual inspection, or first one is the manual inspection, and then you can use it. So basically, the direct methods, and then we learn the indirect methods. So using this, like using cameras or sound, like sound waves, all that we would be finding. So all this looks into all these aspects. So basically, when there's scouring of beds and sites, there's some damage which is going to happen to the uh, pipe or the facility that we are going to be laid. So that will be checked, and damage to drain structure also. If there's a leakage which is there, or if, say, if you remember, in one of the images in our slides, we discussed about how there was a pipe and how a tree root had penetrated into the pipe. So this is a damage which is caused to the drain structure. So that also, by using these inspection, we find it and we will remove it or do adequate maintenance which is required. So that's why regular inspection is important also, because such damage which is happening can lead to blockages as well as uh, leakages of water and all that. So that's also very important. So all the three are right. So option D, A, B, C, all three options are right for this. Okay, let's proceed further. So yeah, so this is the slide which we were talking about all this. So yeah, so all the three stormwater facilities has to be checked for scouring of beds and sites, full or partial blockage of the drain, and damage to drain structure. So this is and we also learned about the times when we do, like before, during monsoon, and post monsoon also. And then during monsoon, if it's difficult, mostly it's very difficult, so that time it's not done. But pre monsoon and post monsoon monitoring is very much important. Okay, so let's go to the next question. So gutters, inlets, and outwall structures must be cleaned in every 1 year, 3 months, 6 months, 1.5 years. This is
1.5 month years.
That's enough.
Yeah.
Okay, so yeah, this is based on standards that we are talking about, like how often it must be cleaned. I agree that in India, probably the frequency of cleaning might be very less, because we always see them to be very not in a very good condition. But the actual time period by which it has to be cleaned is every 6 months. That is every 6 months by uh, what do you say? Uh, as per standards, it has to be cleaned. So this is what we learned in that. So each component, actually, mostly it is like six. Most of the things needs to be cleaned for every 6 months. That is gutters and inlets in every 6 months, outfall structure also in 6 months, even the conduits and manholes in 6 months. So now, only if the pipe diameter is really high, then we will take like once in 1 year or once in 2 years. But otherwise, all the cases, if you observe, by default, it is 6 months. By within 6 months, periodic inspection must be done, and if cleaning is required, it has to be clean. Also, mostly cleaning will be required at that time, so it has to be done. Fine. So let's proceed further. Question 5. Ponding in a stormwater drain can be remedied by. So, firstly, what is ponding? I can hear you.
Ponding is holding water, holding back water, something like that.
Yeah, so by default, it's like water being stagnant or water being in one place. So usually it happens because of some
Yeah.
congestion. That is, uh, what do you say? When there are multiple pipes, like when there's a pipe coming like this, and then there's another pipe which is joining there. Then, if the capacity of the pipe is not adequate enough, then there's ponding. That is, there's a lot of force which is applied over there, and there's some stagnation which might happen. So that is so basically it actually comes out of congestion in the pipes that when there is when the diameter of the pipe is not adequate enough, then ponding usually happens, or when the drain size is not adequate enough, that is overflow might happen because of ponding. So ponding can lead to overflow of drains also. So ponding, how do we remedy is in the question. So first option is by deepening the drain, refilling the eroded or depressed area, and second is desilting and cleaning, provision of grading at every entry points, providing flatter slope with drops. So yeah, so what do you think? How can it be remedied? Oh, sorry. Yeah. Anybody? Okay, so basically, as discussed, it's mainly due to congestion. So we learned about some techniques like where we'll put an overflow pipe so that whatever overflow is there can be taken out. So something like that can be tried. But usually, the first one, deepening the drain and refilling eroded or depressed area, yes, this is a possible method because when we deepen the drain again, that overflow or the congestion which is happening can reduce. And refilling, so ponding, one more reason why ponding can happen is if a pipe, there's some depression in the sound because of some erosion which has happened, then this region also some ponding can happen because uh, because of that wait, what do you say, the profile of the pipe, some water can be stagnant over there. So this can be avoided by refilling this eroded area and making the pipe straight so that water continuously keeps flowing through. So refilling and eroded of depressed area can also be used. Uh, Desilting and cleaning, yes, it helps in increasing the speed of blockages which can happen. But here for ponding, it is not a remedy. Like ponding is mainly because of this congestion or because of the profile of the pipe which is happening. So desilting and cleaning is not an option. Provision of grating at entry points is also not for ponding, and providing flatter slope with drops, that's also not for ponding. So option A is the answer for ponding, that is deepening the drain, refilling eroded or depressed area. Fine. So yeah, so this is what we discussed about ponding over here. Like, so ponding, why it happens is because of inadequate cross section or formation of depression or settling in the bed or bed erosion. So these are the reasons why ponding can happen, and how do we remedy it is by deepening the drain or refilling of eroded area. So this is as per standards. Which, so all these so other desilting and cleaning is mainly because is used as a remedy for blockage due to debris and vegetation, and flatter slope is used for erosion of bed and cross section. To avoid that only we use a flatter slope. Fine. So let's proceed. So question 6, we are talking about for taking sewer line below a road or rail or a canal or a railway line, following types of appurtenances should be provided. So this is it's an extra question which was not there in the previous assignment. So, but it's a very important question also. So, Supriya, I think you're the only person who is very active in answering, so I might keep calling you.
I'm active so that I can learn here only.
Okay.
After office, I don't get time. Even exam is also very near, and I'm enrolled for two of the
Yeah,
courses. That's why.
transportation also. No, yeah.
Yeah. So I try to grab here only whatever I
Oh,
can.
good. So interaction is the best way to grab maximum input.
Yeah, retention in mind is better.
Okay. So do you want to attempt this question?
Yeah, 1 second. Not sure. You can explain.
Okay. So let's go by each
Maybe
one.
inverted siphon.
Okay, so you say maybe it's an inverted siphon. Fine.
Yeah.
So let's go by each. What is a stormwater relief work? What are siphon spillways and jumping where? So yeah, so some of these things we've not discussed much in our lectures, but this was a gate question, so that's why I thought I would put it here. So yeah, so a stormwater overflow or a stormwater relief structure. This we have already discussed. So you have multiple junctions. So you have an overflow pipe also, so that excess of water, if it's there, to avoid that congestion, it overflows outside. So these are commonly used for stormwater relief works, and it consists of a masonry chamber having one overflow weir or a pipe which takes the water outside, and the extra quantity of sewage from the main sewer flows over the weir and goes into another overflow sewer which carries directly to the natural water courses. So some that interaction happens over there, and usually the top of the main sewer is open and the surplus water falls out over the weir, and the overflow waste may be single acting or double acting depending upon the quantity of the flow which is there, and generally the top of the weir is fixed. Okay, so these are some details which is not required. So the whole concept is that, so if you observe over here, the level is different. So from here it's overflowing. So two things are happening over here. This pipe is taking it to the other nearest water body. There's another pipe taking it to another water body, and if you look, the height, there is a height difference also. So this is a stormwater overflow structure, which is a type of stormwater relief work. Then we also have something called as a siphon spillway. So in this, what happens is, and why it's required is because mainly stormwater overflows requires a considerable length of sewer to be replaced by masonry chamber, which results in high initial cost. So we need something like this so that there is a junction, and that water is there, and from there it's going. So to avoid this, to overcome all these difficulties, a siphon spillway is used, which is very effective and has a high capacity than stormwater overflow wells. So what is this? A siphon spillway is a very sensitive and automatic in its action and removes more volume of extra sewage in less time. So this is how a siphon spillway works. So the image is a bit more clearer. Yeah. So you have something like this, and embankment is made, and from there water is allowed to go to the nearby water body easily. So this is a siphon. So you're basically siphoning it through this particular pipe that you have, and you're pouring it out to the nearby water body. So that is a siphon spillway. And then you have these jumping wires or leaping wires. So this is a stormwater relief work which falls under the sanitary sewer through an opening provided on its crown. So an excessive quantity of sewage leap or jump across the opening. So basically, if you have something like this, you have an opening here, and whatever is excess, it jumps out, but whatever is there, it basically comes into. So that is the jump. When the discharge increases, velocity increases, due to which more quantity of sewage jumps over the gaps and goes to the outfall. So it's again the same overflow mechanism. And now comes our inverted siphon. So this is basically, if you have a pipe, so it's an inverted siphon. You're creating a tunnel so that water can be channeled and taken. So as can be seen from the structure, it can be used where there's a valley, there's a roadway, or even if there's a water body on top, so that our pipes can be laid in such a way that it can be siphoned out through this method. So this is an inverted siphon, and for railways, this is the most common method that we use. So this is also called a depressed sewer. So yeah, so Supriya, you were right. So the answer to this particular question is it is an inverted siphon. So for rail, road, canal, railway line roads, water bodies, everything we use. A water body you can directly throw into the water body, but if you don't want to throw it there and if you want to carry it to a different region, then yeah, so you have an inverted siphon over there. So yes. So going to question 7, the design period of a pumping station is how many years? Any guesses? Anybody? Okay, Supriya, any guesses?
It is 15 or 20, more about 15 years.
Okay, 15 or 20. You say finalize on 15.
Yeah.
Yeah, it's right. So this we've already discussed before when we were talking about pumps and pump houses. In one of our previous lectures also previous tutorials also we had discussed for pumping it's always 15 years. Even when the design period is 25 to 30 years, the pumps or motors usually last for 15 years. So pumping station, the design period is usually 15 years because some maintenance inside the station will also have to be done if you're changing the pumps. So yeah, so this is what we discussed in the lecture. So pumping is required. Yeah, so the design period is usually 15 years, and we also discussed where pumps will be used, like in low-lying areas where gravity is hampered, basements, ridges, to achieve self-cleansing velocity treatment plants and outbound river. So this is important. You can keep this in mind because one of the questions which will be coming up, we might this point might be important. So yes, so let's proceed. Yeah, so this is one more numerical. So this is an additional numerical which is not there in the previous assignments, but we're doing this from the examination point of view. So what is the area required for a sediment basin where the particles have a settling velocity of 0.5 meter per second if the maximum inflow through the basin is 2 meter cube per second? So firstly, what is a sediment basin? Any guesses? What is it? What will by name? What does it suggest? A sediment basin. What does it mean?
It's for settlement of particles. Maybe similar to pond, you can say.
Exactly, yeah. So it's similar to that whatever we discussed before also. So basically, in ponding, we have to avoid it. It's some congestion or due to erosion, something is happening. But here in a sediment basin, mainly the design will be something like this. When the water or water flows, uh, storm water always contains a lot of particles in it. It carries soil, other clay, other particles in it. Some of these are which we want to remove them. So a sediment basin is mainly used for this filtration process. So in such a case, like most of the sediments get deposited over here, and it's only the water which, like if you have some structures, like we have artificial methods of doing this also, but sediment basin is a more natural way where you have a natural compacted region. Yeah, some amount of it's a natural formation basically. So yes, I'll just write it. So it's a natural formation, but then we do some compacting on that. So where we compact and we make it in such a the soil compacting is done in such a way that all the deposits which are there in the water gets deposited over here, and it's only the water which flows further onto uh, through the drain. So yeah, so this is a sediment base. So for this to happen, you need to consider certain factors. Like for instance, what are the particles which are coming, or what velocity with which these particles settle down. Like for instance, if it's a particle has a higher mass, then at very low velocities, it probably settle down. But then if it has a greater mass, then this will the set velocity like at a different velocity only it will settle down. So a settling velocity for each particle is also associated with a settling velocity. And also what is the inflow which is coming in. So those are the two factors which is given. So you've been given the settling velocity, and you also have the inflow. That is how much quantity of water is coming through these pipes. So if the pipe flowing full, or is it flowing only half full? Like what is the maximum? Like when the pipe is flowing full, how much is the maximum inflow which is coming, and how much would it be required, like how much so the question is asking what is the area. So considering these two factors, that is the settling velocity and the maximum inflow which is coming, we have to design our sediment basin so that yes, so we have to design a sediment basin so that that particles settle down over there and only the water moves forward. So this is the question which asks that. So Any idea how we would go about it? Or let's say, will the area be, will settling velocity be directly proportional to the what area, or will settling, like if the settling velocity is higher, then would we need a larger area, or if the settling velocity is low, would we need a smaller area? Like what is the relationship? Any guesses? We have learned this formula in our lectures. Okay, so this is inversely proportional. So as the settling velocity increases, then the area required will be lesser. Because, yeah, so area required will be lesser. And we also have the quantity. So as the quantity of water which needs to flow increases, then the area required will be more, because obviously we have more quantity of water coming in. So we need more area to cater to that. So this, and then we also have an adjustment factor, which we will be, so to remove this, we will be having an adjustment factor, which is 1.2. This is mainly based on the turbulence. So we have learned about turbulence in the lecture. So as the turbulence increases, the design aspects, how we need to consider that also we have. So this is again, turbulence is a, we measure it by using a Reynolds number. And also, let's not go into those details. So this is a factor which is based on turbulence. So it can be 1.2, 1.5, 1.7, based on difference. So if it's highly turbulent, we use a different factor. So mostly by default, we are considering 1.2 in our lecture. We have learned it as 1.2. So the formula would be 1.2 into Q divided by the settling velocity. So this is the formula which we would be using. So if this is the formula, then can we say what would this be? So area would be, so what is Q? Q is given to be maximum inflow which is happening is 2 meter cube per second. So 2 meter cube per second divided by, okay, so into 1.2, I'm just writing the factor over here, the adjustment factor for turbulence. And the velocity is 0.05, sorry, zero point 0.5 meter per second. Yeah, settling velocity is 0.5 meter per second. So what does this work out to?
4.8.
4.8 meters square. So this is meter per second. So this is meter cube per second. So finally it will be meter square. So sorry. Yeah, so this is the answer. So if this is so what, which option will be right if this is the answer that we are getting?
5.
5,
D
yeah,
option.
right. So also, if this was 4.5, even then we would still go for 5, because this is the minimum area which is required. So whatever we are getting here is the minimum area. So any value which is greater than that value is what we need to take. So we cannot take 4. Like even if it was 4.3, we cannot round it back and take it as 4, but we will have to go to 5 square meters and take the higher value. So that is understandable. Fine. So let's proceed further. So yes, so question 9 talks about choose the incorrect statements from the following. Stormwater inlets are placed at the minimum spacing greater than 10 meters and maximum spacing less than 30 meters. Uh, Two catch basins must be provided for every three water inlets. Rising portion of an inverted siphon should be less steep to prevent deposits, and pumping stations of stormwater is necessary to avoid overflowing and waterlogging. So, yeah, so any guesses on which is the answer for this?
D is incorrect.
B is incorrect. Okay. Two catch.
D, not B,
D
not
is
D.
incorrect.
Last
Okay,
word.
okay. D. Pumping stations of stormwater is necessary to avoid flooding and waterlogging. So that is incorrect. Okay. What about the first one? Let's go by first one. Stormwater inlets are placed at a minimum spacing greater than 10 meters and maximum less than 30 meters. Is it correct or wrong?
That is correct.
Okay, so that is correct. Fine. This we have learned in our storm water. We have not in this lecture, in the previous lectures we have learned this. So yes.
Yeah.
And B, two catch basins must be provided for every three water inlets. Others can also attempt the question if, or you can even put it in the chat box. Mr. Harish, ML, anybody can attempt. It would be nice if there's more interaction. Okay, so let's discuss on this. So, okay, so two catch basins must be provided for every three water inlets. So, Supriya, are you back? Okay, no. So, what is a catch basin? Like, so here, the first one, yeah, because we've discussed about
Yes,
two.
I'm back.
Yeah, cool. So, what is a catch basin over here? Okay, so catch basin is any when you have a water supply pipe coming, so you have a basin where you will hold water for some time. So mainly it's used for settling of debris or some uh, debris or some filtration which is happening, like what we discussed before. So retaining the different sediment retaining. So for all these, we can have catch basin. So it's basically a structure through which different inlets join into. So it said that if there are for every three water inlets, you need to have two catch basins. So yeah, so every three you need to have two catch basins is what is said. So is this right?
Yeah, this is right.
Okay, Supriya says this is right. Fine. So let's go. The rising portion of an inverted siphon should be less steep to prevent deposits. Is that right?
I guess yes,
Yeah,
but
so
not
this we've
sure.
discussed. Like we discussed ponding. So we discussed that when for ponding to happen, we need to rise it. The erosion and all those should be removed so that the pipe is straight. So in this case also, if the steep is very if there's a very high steep, then water will not go. We would need additional pumps. We for this also we would need pumps in order to pump water up. Whereas if the slope is not too much, then water can with the velocity self velocity itself it may even go or pump requirement also reduces. So this is right. That is the rising portion of an inverted siphon should be less steep to prevent deposits. Otherwise, there will be more deposits which are happening over there. Right. So this is right. Now, second one, pumping stations for last one, pumping stations for stormwater is necessary to avoid flooding and waterlogging. So, Supriya says this is wrong, but let's just go back to our here. So yeah, so here we discussed about pumps are located for low-lying areas where flow by gravity is hampered. So again, coming back to this, so this is required like in stormwater to avoid flooding and waterlogging. So what happens in these low-lying areas is it can even lead to flooding and waterlogging because of adequate water not being pushed up because of that. So you need pumping stations. So this is actually right. You need pumping stations as pumping stations are required to avoid. So when there's some flooding is happening, you can use a pumping station in order to remove that water outside. Or when there's water logging, like by naturally, so as we discussed over here, naturally if the water is incapable of going through that particular channel, we need pumps so that we'll push the water forward. So the last answer is right. The answer which is wrong, here we have to mark the incorrect statement. So the answer which is wrong over here is two catchment basins must be provided for, excuse me, yeah, for every three water inlets. This answer is wrong. We just need to provide one catch basin for each water inlet. So, I mean, yeah, it's a bit tricky because we might not notice this, but yeah, we just need one. Like for uh, 3:1 is the usually what we follow. So, yeah, so we have it over here. That is one catch basin for every three inlet is what is required. So yeah, so again, this details out the stormwater inlets. Yeah, catch. It's a type of inlet structure for retaining sediment and debris transported by stormwater, and we just need one catch basin for every three inlets which are coming in. Okay, so let's proceed further. Question 10. Dash helps in flood forecasting, design of spillways, reservoirs, and flood protection works by predicting the changes in shape of a hydrograph as water moves through a river channel or a reservoir.
Hydraulic routing. First
Okay,
one.
hydraulic routing. So, okay, yeah. So, what is hydraulic routing again? I mean, what is designed over here? So, it basically looks into the changes in the shape of the hydrograph and as when the water moves through a channel, and that is used in order to design. So, what are the other things? What is a hydrograph? We have discussed this in our last tutorial. So, if we have something like this in a hydrograph, what will be in the x-axis and what will be in the y-axis? Let's recollect.
Runoff, it was used to measure runoff something.
Yeah. So you have rainfall runoff. Yes. So you have rainfall, what is happening in millimeters, which will be in the y-axis. And here you will have time, like that is in what time that runoff is reaching the mouth or the area of excuse me, area of concentration that we are interested. So, like if you have 0, 10 seconds, 20 seconds, so it just goes on like that. So that is a hydrograph. And what are isochrones?
Cannot recall.
Yeah, so isochrones basically, if you have an entire catchment area, the area is divided, and if you have your mouth of the inlet over here, the area is divided into certain portions so that that based on the time, area is divided into certain portions based on the time required for water to reach. So, regions, water from the same isochronic locations will reach this outlet in the same time. That is, from this region, it will take probably 10 seconds for water to reach. From this region, it will take 20 seconds for water. So this belongs to a different isochrone. From this region, water takes about 30 seconds to reach. So this belongs to a different isochrone. So it's like a contour mapping. So based on in contours, we have regions with same elevation points, right? So here it's the regions where water takes this much of time to reach. So based on that, we mark. So those are isochrones. And what is a unit hydrograph? So unit hydrograph is for every 1 meter, 1 unit, how much, not meter, 1 meter square. That is for 1 unit, how much of water is coming. So from that one area, how much is water is being collected. So that is a unit hydrograph. So we make a graph based on that. So yeah, so Supriya, for exam point of view, maybe you can revise these in detail. That'll be helpful because these are very important points which might repeat also in the coming lectures also.
Yeah, okay.
So yeah, so so this is what we were talking about hydraulic routing of stormwater receives. So yeah, so this we have already discussed. So I'm not going into the detail. So yeah, so question 11 talks about choose the correct statements from the following. Lesser the surface area of the channel, lesser the lining cost and more hydraulic capacity. And semicircular channel has a minimum hydraulic capacity with maximum surface area. Trapezoidal section is of high cost and is difficult to construct. Natural channels need to be stabilized to carry the stormwater runoff in urban areas. So yeah, so let's go option by option. First one, is it right? So the question is asking
Yes,
choose a correct.
A is right.
Okay, so A is right. Why? Lesser the surface area, less of the channel, lesser the lining cost, obviously. So this part is correct. And will the hydraulic capacity increase? Like that is also right.
A bit confusing for
It will, it will.
me right
So
now.
because here we are mainly talking about like if you have a rectangular section, trapezoidal section, circular section. So this has a least. Okay, so let's, yeah. So basically the hydraulic capacity will also increase. Let's look into the second question. So, second option, semicircular channel has a minimum hydraulic capacity and maximum surface area. Is that right?
No, maximum surface area
So it is
is
maximum and it has the minimum surface area. So when you have a circular section, you have minimum surface area and it has maximum hydraulic. So yeah, so these both are interlinked. So compared to a rectangular trapezoidal section, so if you take a circular section, then the area is reducing. So area is reducing, lining cost is reducing, and our hydraulic capacity is increasing. So first option is right. So it will have more hydraulic capacity also. So this is right, this is wrong. What about the third one? Trapezoidal section is of high cost and is difficult to construct.
yes, this is correct.
Okay, so Supriya says this is correct. And what about D? Natural
Cost
channels.
is high,
Hmm.
but difficult to construct. I think this is true. So Now
Yeah, but
next.
if you have an and clause, then if both are any one is wrong, then we will mark it as wrong, right? Oh no, if yeah. So this is choose a correct option. So both needs to be correct. So you're saying cost to correct is
Yes.
high, difficult to construct is also high. Right. Fine. So
Yes.
last one is natural channels need to be stabilized to carry stormwater runoff in urban areas. Do they need to be stabilized? Firstly, what do we mean by stabilizing?
No idea.
Yeah, so natural channels, they're natural formations. So before stormwater can be passed, stormwater runoff, if you want to carry it them as a stormwater drain or a sewerage, then we need to stabilize them so that more erosion does not happen. That is, if you do, by stabilization means you compact it and you make them more stable. Like by natural, if it's a natural profile which is there, then when water is running through this, then there are high chances of this soil to fall into the drain that we are taking stormwater in. So even if it's a natural channel, we need to stabilize it or we need to make it more compact and make it into a proper drain before stormwater runoff can be before it can be used to carry stormwater runoff. So this is right that you need to stabilize it. So if this is the case, then I think we're not getting the options right. So something is wrong. Like either A is wrong or C is wrong or D is wrong. Something is wrong. So make a call on that. Okay, let's see what is wrong. So the option D, that is natural channels, has to be stabilized to carry stormwater. So this is right. Now, next one, where it comes to less surface area, less is the lining cost and more is the hydraulic capacity. So this is also right. We've discussed this in detail in our lectures. And when it comes to semicircular section, maximum hydraulic capacity with minimum surface area. So that's why our option B was wrong. And trapezoidal section adopted mostly due to the low cost and ease of construction and almost similar to semicircular in shape. So why? Because you have a trapezoidal section, so when water flows, it kind of resembles to a semicircular section itself. So that's why this is the most preferred. To construct a semicircular section, it will be more expensive, whereas to construct a trapezoidal section, it will be much cheaper because it's much easy. If you want to make a profile, then to keep the casting and everything, this is much easier because it's all straight lines. Whereas if you want to create something like this, if it's an RCC or even to provide a lining, this is much easier compared to creating a semicircular profile. So yes, so this option, that is our option C, is actually wrong. That is, it it has a low cost and it is easy to construct. So this is wrong. So the answer for this one is A and D
No,
are
no.
incorrect.
For trapezoidal cost will be high.
Let's see here.
Right
Trapezoidal
second.
section cost is low.
Low. Okay. Okay. Okay.
Yeah, no, okay, so let's reason it out why the cost is low because, okay, maybe compared to a rectangular section, if you're saying a trapezoidal, but if you're comparing it with this one, semicircular section, the ease of construction is much easier for a trapezoidal section because you just need to keep the mold in such a way if it's an RCC channel that you're using, or even if it's a yeah, RCC channel. Mainly for this one, we'll be using an RCC channel, right? So it's much easier to construct this than to construct a semicircular section. Yeah, and it's almost similar. The shape, like whatever we are getting, is almost similar to us, like the water flow when it behaves like a semicircular section also. So yeah, so it's option A and D. So A and D, the option D, this is the right answer for this. Right. So let's proceed further. Yeah, question 12. This will be the last question. Sewer cleaning is undertaken on a scheduled basis to reduce blockages, to remove deposits, to minimize odor, or to trap gases. Okay, so reduce blockages. Is it right or
Yes.
wrong? Right? Yes.
Right.
Okay, so it is right. To remove deposits,
Yeah. Right.
right. Minimize odor,
Not sure. D is right. Trap gases. Maybe. A,
uh,
B, D.
ABD is what you're saying. ABD is what you're saying. Okay, so let's see. So this is what we have learned for that. So yeah, so sewer cleaning is undertaken on a scheduled basis to remove deposits, right? To reduce blockages per unit length and to minimize odor. So for these three, we mainly use. For trapping gases, we don't use because actually we don't need to clean the sewer to trap gases when you're reasoning it out also. In order to remove the gases which are there, we might give grills or we might give certain pipes like this so that gases can come out. But we don't have to clean it in order to trap gases. That's not required. So A,
Okay.
B, so it's A, B, and C, which is right. So option A, which is right. This is wrong. You don't have to trap gases using. You don't have to clean sewers in order to trap gases. We already, while designing itself, we provide a mechanism by which gases which are trapped inside can be escaped outside. So that mechanism is already provided. Fine. So yeah, so that's all for this week's discussion. If you have any doubts on anything regarding the lectures, assignments, anything, you can ask now or we can wind up.
No,
No doubt.
so thank you. No
Okay.
doubts.
Yeah, fine. So thank you all for attending today's lecture. Hari sir, are you saying something?
So thank you. I said thank you.
Oh, okay, okay. Yeah, fine. Okay. So thank you all. So see you all next week with assignment 11 and all the best for your exam preparation also. Bye.
Thank you. Bye.